In this series of videos, we're going to be introducing the differences in formation, structure, and naming identification between covalent compounds and the previously discussed ionic compounds. Firstly, we actually need to explain what the word covalent means, because this is the key distinguishing feature between covalent compounds and ionic compounds. Firstly, unlike ionic compounds that form between some combination of metal and nonmetal or metal and polyatomic ion, covalent compounds exclusively form between two or more nonmetals. For example, we can see both hydrogen and carbon are nonmetals, and likewise hydrogen and nitrogen are both nonmetals. The biggest difference, however, between covalent compounds and ionic compounds is in the attractive force that holds the atoms together. So unlike in ionic compounds, where one element gives away its electron and the other element receives that electron, where charge is what holds the two atoms together, covalent compounds are held together through the sharing of electrons that exist between the two compounds. For example, we can see that this unpaired electron and this unpaired electron can together form a pair, and this mutual sharing of electrons is what holds hydrogen and carbon together, and likewise with hydrogen and nitrogen in this pairing here. In terms of the technical descriptions or technical vocabulary for what exactly is going on here, we can see in order to join multiple nonmetals together, each element needs to have at least one unpaired electron in order to engage in sharing. And when, say, hydrogen in this example shares its unpaired electron with one of carbon's unpaired electrons here, this forms what we call a covalent bond. And again, we can see the word valent here is in reference to valence, because obviously the electrons that are farthest away from the nucleus in the valence shell are the ones that are directly involved in sharing, and co is a prefix that means with, or perhaps more accurately together, as in the English word cooperate. That means that each of the unpaired electrons is together shared between the two elements that are joined together in the covalent bond. Now, when two elements form as many covalent bonds as are required in order to form a full valence shell, we represent each of the bonds with a single line that connects the two atoms together. So if we zoom in on the structure of CH4, we can see that there are four lines here, and each of these lines represents two electrons. One of these electrons came from hydrogen, and then the other electron in the pair came from the carbon in the center here. Now, this principle applies to all covalent compounds, but the combination of bonds and what we call lone pairs is what potentially changes. So recall that nitrogen in this Lewis structure here only has three unpaired electrons like this, and the last pair of electrons that already exists as a pair before it forms bonds with hydrogen is why we call this a lone pair of electrons, because this pair of electrons belongs only to nitrogen and isn't shared between two elements. And most of the time, there are some interesting exceptions to this, but most of the time, lone pairs are not involved in bond formation, and we can see that the lone pair of nitrogen as an element remains as a lone pair in the compound NH3, and then the remainder of the bonds form when hydrogen and nitrogen share each of their unpaired electrons like so, resulting in three bonds. Where this gets more interesting, however, is if both of the elements, or at least one or more of the elements involved in a covalent compound, has more than one unpaired electron. Previously, we've only involved hydrogen here, which only has a single unpaired electron, which means that hydrogen can make a single bond. But here we can see, in the case of CO2, that both carbon and oxygen have more than one unpaired electron, and this results in a phenomenon that we call multiple bonds. For example, if we want to connect carbon and oxygen, we can see that there's a pair of electrons here that can form a covalent bond, and here there's another pair of electrons that can form a second covalent bond, and likewise for the other oxygen here. And when we realize this, remember that we represent each shared pair of electrons with a line in the overall structure of the covalent compound. So that means that there would be 2 electrons for this bond on top and another 2 electrons for this bond on the bottom, representing 2 different sharings of unpaired electrons like this. And here we can see that this creates a phenomenon that we call double bonds. So a double bond is a situation where one atom shares 2 pairs of electrons with another atom, as we see in CO2. Now, as we will see with many nitrogen-containing compounds, triple bonds also exist. So if we want to connect carbon and nitrogen, we can see that we can get, this is going to be a little bit awkward, one covalent bond here, one pair of unpaired electrons shared, one pair of unpaired electrons here, and the last pair of unpaired electrons we can see here. And if we realize this in a proper covalent Lewis structure, that means that there's 2 electrons for the bond on top, 2 electrons for the bond on the bottom, and 2 electrons for the bond in the middle, resulting in a triple bond that we see here. And then carbon's last unpaired electron can then form one additional bond with the hydrogen that we see here. So even though the formation of covalent bonds happens more or less identically, no matter what the nonmetals are, we can see that we have a lot more flexibility in terms of bond combinations. For example, we can have bonds and lone pairs depending on which elements already have lone pair electrons, and we can also have multiple bonds, double bonds and triple bonds, a phenomenon that hasn't been seen in ionic compounds. This results in a number of complications, which is why many people consider covalent compounds to be much more structurally complicated than ionic compounds. So previously, except for when involving transition metals with more than one charge, previously there was only one way to write a chemical formula between a metal and a nonmetal, but here we can see that there are many different varieties of compounds that can be made only using 2 elements. For example, all of these elements here contain only nitrogen and oxygen, just in different number, and as we can see, in different bond arrangements. And probably the most extreme example of this is when we can create multiple compounds involving carbon. In fact, carbon is so good at creating multiple different covalent compounds that there is an entire branch of chemistry just devoted to the way that carbon, hydrogen, and usually oxygen bond with each other, and this is what we call organic chemistry. So if you often see carbon compounds that contain hydrogen labeled as organic compounds, this is why. This concludes our first video looking at the basic structure and mechanism of formation of covalent bonds and the compounds that contain them. In the next video, we're going to take a more detailed look at how Lewis structures of covalent compounds can be drawn using a reasonably systematic procedure.